I'll just kick it off and talk about an introduction to river ice processes. So in this section, we're going to start with the physical properties of water and ice.
Started the meet. Grab yourself a chair.
Okay. Yeah, so we'll start with the physical properties of water and ice, and then we'll move on to ice formation processes. So we'll cover thermally grown ice, which will include a discussion of border ice. Then we'll cover Frazil Ice, starting with seed crystals. We'll talk about anchor ice and dynamic ice cover formation. Next, we'll talk about sheet ice, and then we have some material on the formation of ice and steep streams that we'll cover. So this is the obligatory big picture slide showing the phase diagram for water. This figure shows a very broad range of temperatures on the x-axis and pressures on the y-axis. So liquid water is in green, ice is in blue, and water vapor is in yellow. Of note, there's actually a lot of different forms of ice characterized by their crystal structure. Here on Earth's surface, we experience a very small range of these temperatures and pressures, essentially what's inside the little black box there with the arrow pointing to it. In cold regions hydrology, we're primarily concerned with liquid water and what's called ice 1H, the only form of ice that's naturally found on Earth. So there's a big world of water, but we're concerned with a pretty important end of it. Next, we'll move on to the density of water. So the density of water is pretty interesting, temperature dependent. Just to let somebody know there's a hot mic out there, so if you could just make sure everybody's on mute, that'd be great. So yeah, again, the density of water is interesting. It's temperature dependent, like most substances. As the temperature of water decreases, its density increases as the water molecules get packed closer together. But something curious happens at around 4 degrees C. As shown on the plot here, the density doesn't continue to increase below that temperature. In fact, the density decreases a little bit. The simplified explanation for this is really simplified, but it's basically that the water molecules start to line up in orientations that will eventually form the lattice of ice crystals. So they're kind of getting set up to get into ice crystal formation. And that pushes them apart from where they were at 4 degrees C. So you can see the temperature density curve of pure water also as it declines, it actually extends beyond 0 degrees C to the left, so past the freezing point. Water in this range is referred to as supercooled water. We'll talk about that later in this presentation. It's an important property that we'll talk more about. But even after the phase change from water to ice, so when it's in a solid state, ice is less dense than water in its liquid form at 4 degrees C. That's a pretty important aspect of water or feature of water. So is this odd density behavior important? Yes. It's actually why lakes and ponds don't usually freeze to the bed, although they definitely can. We see this in the Arctic, of course. But by and large, they don't, and that's really important for supporting biological processes, which is outside the scope of what we're going to talk about, but it's a really important aspect. It also affects the ice formation processes and how ice forms and evolves. Because of the density variation of water with temperature, water columns can become what we refer to as stratified. So in the summer, when the bulk temperature of the water is greater than 4 degrees C, the warmest water is sitting on the surface. That's the least dense water, and it tends to stay there and get warmed up by the sun, and the warmer water stays on the surface. In the winter, when the bulk water temperature is below 4 degrees C, the warmest water, the most dense water, is actually at the bottom of the water column. So it's kind of opposite. And the coldest water sits at the surface, and further cooling, release of heat into the atmosphere will cause the density to decrease. Further in it, it'll stay there at the surface, which will eventually result in ice formation. So this figure here, this little diagram on the bottom right, is just an example of what a stratified water column could look like. There's a lot of variations on this, but you could end up with 0 degree water on the surface and 4 degree water at the bottom. So there's one really big caveat to this process. It requires relatively quiescent or slow moving or stagnant water. The density variation below 4 degrees C is relatively small, as you can see on the y-axis of the plot here. So the stratification can be disrupted by mixing processes such as wind or river currents, which produce turbulence. In nature, we experience two typical ice formation cases, although these can be present along the same river or at the same location at different times, depending on the environmental conditions. The first is ice formation in thermally stratified water columns, like what we were just talking about. Ice will form on the surface at some point after the coldest water on the surface reaches the freezing point. The other case is for well-mixed water bodies where the turbulent mixing processes blend the water such that there's essentially a uniform temperature throughout the entire water column. So many rivers will fall into the second category, though individual reaches may not have much mixing. Stratification can occur. Lakes and ponds that are exposed to wind may not stratify if wind-induced vertical currents are sufficient to overcome that density variation. So there's no hard rules here. So on the first slide, we discussed the phases of water. Obviously, water can move between these phases from liquid to solid to vapor in different ways on different pathways. In river ice processes, we're most preoccupied with the phase change between liquid and solid, between ice melting and water freezing. Phase change into vapor can be important for some cold regions, hydrology, for example, sublimation is important in snowpack evolution in the Arctic. But for the purposes of this discussion, we're just going to mainly focus on ice and liquid water. So water has energy stored in it. Removing that energy or removing heat from the water will cause it to cool, and adding heat will cause it to warm up. That's pretty intuitive. The specific heat or the heat capacity of a substance, that describes that relationship between heat being added or taken away and the resulting temperature of that material. So the specific heat of water near the freezing point is about 4,200 joules per kilogram per degree C, which that means that 4,200 joules of energy exchange are needed, either added or taken away, to heat or cool 1 kilogram of water by 1 degree C. So to put that into context, there's a few other materials here we have the heat capacities for. Ice, as we'll discuss here in a minute, has about half the heat capacity of water. And then just some other items, air, aluminum, sand, have about a quarter of the heat capacity of water. So that means this is the same amount of heat it takes to warm 1 kilogram of water, 1 degree C, would increase the temperature of ice around 2 degrees, and air, aluminum, or sand about over 4 degrees. So water can be thought of as good at storing energy relative to temperature changes. So if heat is continuously removed from water, say lost to frigid air over a water surface, the temperature of the water surface will decline to the freezing point. It's important to realize that water does not spontaneously freeze at the freezing point. Once you get to zero, it doesn't just instantly turn to ice. In fact, water will continue to cool below that freezing point. We already mentioned this briefly. This is called supercooling, when water is actually colder than the freezing point. So similar to water, I'll just jump back to ice and talk about some of the material properties of ice. The removing heat from ice cools it, adding heat to it warms it. The heat capacity of ice, like I said, is about half that of water, meaning that the temperature of ice will change more for a given exchange of heat than water would. And then once ice is at the freezing point, adding more heat to it will cause it to melt. So far, we've discussed energy inputs or removals and how they'll affect the temperature of water or ice. The other significant energy-related processes are what happens at the phase change point. So latent heat is energy that's stored in a substance that cannot be directly measured with something like a thermometer. Liquid water has more energy in it for a given mass than ice does, even if both of them are at the same temperature, say 0 degrees C. This difference is the latent heat that's present in the water. So when water freezes, it transforms from liquid water into solid ice, it releases the latent heat of fusion, which is about 334,000 joules per kilogram. That's a fair amount of heat. This heat is released into the water and the air and will warm adjacent substances, including the water. So ice formation actually will warm water around it, which is kind of interesting. And this can directly affect the rate of ice formation. And then conversely, ice is in a lower energy state than water. So in order to get ice back into liquid water state, sufficient energy needs to be added to break the molecular bonds in the ice. And the amount of energy that is required to accomplish that is the latent heat of fusion again, the 334,000 joules per kilogram. So of note, during these phase changes, there's no change in the temperature of the ice or water. We've been talking about ice and water both at 0 degrees C. So all the energy we're talking about moving back and forth is exchanged just to change the phase, to modify the molecular structure of the substances. So there's a lot of energy exchange going on at this phase change point. So from a practical standpoint, this means that once ice forms, it takes a tremendous amount of heat or energy to melt it, especially typically all that latent heat is gone. It's either been ejected away or lost to the atmosphere. So you've got this material in a lower energy state that if you want it to go back to liquid water, you need a significant source of heat. Okay, so now back to something a little more tangible. The density of ice is temperature dependent as well. At 0 degrees C, the density of ice is around 917 kilograms per meter cubed. At minus 40 C, it's a little more dense, but it's a change of less than about 1% across the range of temperatures that we see on Earth. So in practice, we typically assume that fresh ice has a constant density of about 917 kilograms per meter cubed. The density of fresh ice is less than that of fresh water, of course, so it's buoyant, which is, of course, a bit unusual for a solid version or solid state of a substance. But it's not a lot less dense. It's about 92% of the density of liquid water. So when it's floating, only about 8% of the ice is above the water level. That's what we sometimes refer to as the freeboard of the ice. The remaining 92% of the ice is submerged. So now we'll move away from some of these kind of basic fundamental physical properties, and let's talk about how ice actually forms in rivers. This is kind of really what we're interested in here. Anyways, so we have a few different scenarios that we can break down river ice formation into. The first is the no ice formation scenario. This can happen even if you've got a lot of the ingredients for creating ice, but if you have high velocity flows where just mechanically ice can't form and then be retained in a fixed location, ice might be formed, but it might just be moving right on through the system. And then we obviously don't get ice if the water isn't cold enough to generate ice, but there are cases where otherwise we have the conditions where ice would form, but locally it doesn't. And that is often because of warm water inputs. So this can be sources of heat from natural processes like groundwater infiltrating into a stream, adding heat to the system, or a human-induced process, such as discharge of cooling water from a power plant or an industrial process, for example. The next category or scenario is ice forming in calm water. We talked about this a little bit. Thermal ice growth is ice forming and growing in slow-moving water. It's typical of lakes and ponds and that sort of thing. And then last, we have ice formation in turbulent water. This is characterized by Frazil Ice formation and Frazil processes, and we'll talk a lot more about that here as we move on. We'll start with thermally grown ice, though. So thermally grown ice forms when there's a persistent period of frigid air temperatures, and the water body's been exposed to those types of conditions, such that the bulk water temp is below 4 degrees C, and probably there's some stratification going on. I've got cold water at the surface and more water down below. Thermal ice tends to be transparent. It's an interesting property, and it can allow solar penetration through the ice cover, and water under the ice can absorb it. That can be an important detail depending on some particular ice formation processes, but it's a little bit in the weeds for this presentation. But it is important to know that solar radiation can still get through ice. It's not opaque, obviously. So once a thin ice cover is formed on a water surface, it will continue to grow as long as heat transfer away from the water continues. So the interface, this diagram shows kind of that schematically. The interface between the water at the bottom of the ice surface is always 0 degrees C for fresh water, and the ice will grow downwards into the water column from that surface if heat is continuously removed from the surface. That heat has to move through the ice cover and is lost to the atmosphere from the ice surface. So increasing ice thickness will slow this process down because you've got more of a thermal pathway to go through. Things like snow cover can also significantly affect this by creating a much longer thermal pathway. Snow's a really good insulator and can really slow down ice growth. Border ice is a type of ice growth, thermal ice growth that you all are probably familiar with. It's ice that grows and forms in slower moving water along the shore or around islands in a river, and extends out into the river channel. It grows both vertically and laterally, so it gets thicker and grows out into the water. Depending on the flow conditions, it might grow completely across a river and close it off just through a thermal process. Or a current in the stream may prevent that from happening if the water might be moving too fast for that to occur. Another process that's pretty common is ice and slush floating down a river can accumulate on the edge of border ice, and you can end up with kind of a hybrid thermal and accumulation process. Like I said, that's pretty common. You've probably seen that if you've looked at some streams with border ice growth. So these figures here are just some examples of border ice in different scales. So now we're going to talk a little bit about Frazil Ice. This is an important type of ice that you may not have heard about, depending on your background. You may have heard about it, but not know much about it, or maybe you've only heard part of the story. But it's a fundamental substance in river ice formation, as we'll talk about. So just a quick overview: Frazil ice only forms in areas of open water. Typically forms in turbulent water, which exists either due to flow velocity or wind mixing occurring. And Frazil ice forms in supercooled water, so water that's below the ice-water interface temperature of 0 degrees C in fresh water. So what is Frazil ice exactly? Here's a definition. We'll start there. It's fine spicules, plates, or discoids of ice suspended in water. That's a little bit wordy. What's a spicule? It's a small pointy object, something we'd sometimes refer to as a needle. You can see larger needle-shaped ice in the top right figure. The initial form of that needle ice would be much smaller, and this has probably grown quite a bit to get to this state. But Frazil ice forms several different shapes besides needles, and actually pretty commonly into plates or disc-like particles that you can see with a microscope or a magnifying glass. And you can see that with the picture on the bottom left, some discoid type shapes of Frazil ice. So Frazil ice is a major player in a larger process of river ice formation that we're going to discuss. So Frazil ice evolves significantly from the moment that it's first created to wherever it eventually ends up. So either it can form an intact ice cover, adhere to the bed. It can just continue to be transported downstream, and eventually it'll melt back into liquid water. So there's a lot of different evolutionary pathways that we'll talk about here. But we'll break it down into some different phases. The first phase is formation, which is made up of seeding and a phase of dynamic growth. For this phase to start, we need to have supercooled water as a prerequisite. The second phase is transformation and transport phase. Frazil ice particles will flocculate together and deposit. They may be transported downstream and can form surface ice covers that can also continue to move downstream. The last phase here that we've broken out is the development of a stationary ice cover. So Frazil can form a continuous stationary cover across the top of a river and then continue to grow as sheet ice. So that's a possibility depending on the environmental conditions. So here's another big picture figure. We're moving from the left to right here in the evolution of Frazil ice. We'll start with the formation phase, highlighted here in the red box. And seed crystals kick off the whole process, and they grow into disc crystals. So we'll dive into that a little bit more. So let's talk about the formation of Frazil ice a little bit. There's a lot to this topic, and some aspects of the process are still poorly understood. We know we have to start with supercooled water. In calm bodies of water, that might just be a thin layer of supercooled water right at the surface. In well-mixed rivers or lakes exposed to wind, that may be a significant part of the water column, or maybe the entire water column that's supercooled. There are a couple of at least theoretical pathways for ice to spontaneously form and kind of kick off this process, this spontaneous ice formation process we call nucleation. So we'll talk first about initial nucleation, which is the first appearance of ice from liquid water. There's homogeneous nucleation, which is the widespread spontaneous appearance of ice in pure water. This has been shown experimentally to occur, you can demonstrate that it happens, and it occurs at about minus 39 degrees Celsius. So the water temperature needs to be about minus 39. So in nature, we only see supercooling in the range of minus 0.1 degrees C. That's a tenth of a degree below zero. So not much, and nowhere near minus 39 degrees C. So we can reasonably conclude that Frazil ice production isn't occurring due to a homogeneous nucleation process in nature. The water just doesn't get cold enough for that to be a possibility. So the other possibility is what's referred to as heterogeneous nucleation. So this is spontaneous formation of ice, usually in a water droplet or vapor cloud around some nucleating agent. So this could be a dust particle, or it could be some organic material like bacteria or a fungi spore, anything really small like that. And there's experimental data that shows that this process doesn't happen in natural water bodies, but it certainly happens routinely in the atmosphere. So the figure on the bottom right here shows the range of temperatures that various nucleating agents form. in supercooled cloud droplets. This all happens below -1 degree C. So when these seed crystals form in the atmosphere, or when these crystals form in the atmosphere, we call them seed crystals. They're an essential ingredient for Frazil Ice production, along with the supercooled water, of course. So practically, they may come from snow. You could get bursting bubbles in the water that produce droplets that then freeze in the air and then return as a seed crystal. Wave action or splashing and turbulent ripples could provide the environment suitable for Frazil Ice generation as well. So once we have the seed crystals in the supercooled water body, they'll continue to grow once they're actually in the river or the lake or the pond. This process of continual growth is referred to as secondary nucleation, and we think that a major part of the process driving this is due to collisions between individual ice particles in the water that cause pieces to break off into small crystals that then grow further. So in suspension, Frazil Ice in suspension at low supercooling rates, Frazil Ice crystals actually grow in pretty uniform thin discs. Here you can see a nice figure of that, these very uniform objects. So if you recall from a few slides ago, we talked a little bit about latent heat. That's the energy that's exchanged during the phase change. So when Frazil Ice forms through secondary nucleation, water getting converted into ice, that water releases latent heat, effectively warming the water. So when the water reaches 0 degrees C from added heat, the crystallized growth stops. So you can see that ice formation can be somewhat self-modulating because all of this is happening it's in the window between 0 and 0.1 degrees below 0. So a pretty small window. But if there is sufficient heat transfer capability out of the system to the atmosphere, so like clear, cold skies, that sort of thing, the process can go on for hours or in some cases days. There's a lot more to discuss about this initialization of Frazil Ice formation. And this is just a brief overview, so hopefully this gives you a little bit of background on the first part of this process. So this is a cartoon of the whole Frazil evolution process that we're discussing. So far, we've just been talking about what's going on in this first red box, which is just the formation of initial Frazil Ice. The crystals form usually near the surface, but entrainment of the crystals can get them down into the flow through turbulent mixing, allowing for secondary nucleation to occur throughout the whole water column. So next, now we've got Frazil in suspension, we'll move on to the transformation and transport processes. So the exact pathways that the Frazil takes depends on the environmental conditions, and many of these processes may occur simultaneously. The Frazil Ice particles will tend to flocculate together, so they kind of clump up, or in some cases, they'll adhere to the bed. If the current allows, the Frazil might just continue being transported downstream. It doesn't have to go to the top or the bottom. It can just stay suspended if there's sufficient turbulence to support that. And surface ice accumulation of Frazil can evolve into larger forms, which we'll talk about here in a minute. So first we'll start with Frazil and suspension that can accumulate to the bottom of the stream. This is what we call anchor ice. This is a depositional process. The mass of ice that forms on the bottom is a mixture of both ice and water. So it can allow some flow through it. It's somewhat porous, but not very. And it can significantly affect the stage of a river because it isn't really that permeable. Although it starts out as a depositional process, if the water at the bed is supercooled through this turbulent mixing process, the anchor ice can grow thermally as well. So ice can grow on top of the thermal ice anchor ice accumulation. Anchor ice is often quite transient. It will release if the environmental conditions change, sometimes even just a little bit. Oftentimes it will form on clear, cold nights when heat loss to the atmosphere is maximized. And then when the sun rises, a little bit of additional solar radiation coming in is enough to cause it to release. So anchor ice may persist for long periods of time in steep streams where there might be more shading and there's more complex bed structures that can help mechanically support the ice staying in place. Anchor ice is something that usually forms just at the surface of the substrate. It's not, like a frost or something. It doesn't tend to go deep down into the bed. In steep streams, anchor ice can continue to grow and form ice dams, which we'll talk about at the end of this presentation. So here's just a few examples of anchor ice in smaller steep streams. You can see the presence of ice significantly changes the channel bathymetry and will cause the stream stage to rise, even though the discharge isn't necessarily changing and probably isn't, it might even be declining if it's in recession. There's a few more examples. On the top right is an example of an ice dam. And on the bottom left, we see the ice appears to be largely submerged and intermingling with the gravelly substrate. The term anchor ice is sometimes used to refer to ice forming on submerged objects besides substrate. So in this example, this is a chain that's covered in ice. It can also form on trash racks of water intakes for power plants or municipal water supplies. That's a whole topic for another discussion. And we do quite a bit of work on that here in ice engineering. An interesting aside or aspect of anchor ice is that can actually play a role in sediment transport. Here on the right is a couple pictures showing embedded and transported gravels that were moved when anchor ice formed around them, and then something changed. The anchor ice released, became buoyant, and then moved downstream and carried this gravelly substrate with it. So that's just kind of an interesting process. Okay, so we've talked about deposition. Now we're talking about the other direction. If Frazil ice forms slush and rises to the surface, it can evolve in shape and size depending on the river environment. So this kind of manifests as what we call Frazil slush, and these are just a couple examples that should be pretty familiar to anybody who's looked at rivers, particularly on very frigid days. These are flocks of ice that are loosely connected, and if you kind of reached in and scooped them out, it'd have kind of a coarse, granular structure, kind of look like slush. So yeah, these are just some examples of a stream in Vermont and a stream in China. You can see a lot of similarities, just these loose flocks. So I alluded to this in the last slide, but in higher energy systems, the Frazil slush might just continue downstream, more or less in this kind of loose form. It might grow a little bit as it moves along. In medium energy rivers, but still relatively steep, we see the formation of pancake ice commonly. These are also seen in bodies of water where there's a lot of wave action. These Frazil ice flocks join together into distinct accumulations that then interact with other accumulations surrounding them. And these interactions, these collisions, will tend to cause the ice to form these roundish shapes, hence the term pancake ice. In rivers with relatively low energy, mild slopes, the ice will form into large flows that may span a significant portion of the river, but they're still moving downstream. So here's an example of the Yukon near Dawson City, where you can see these big ice flows moving downstream. Here's an example of some pancake ice on the Mississippi River. You can see here the rounded edges from the collisions of these accumulations together. Here's an example of one of those close up. We've got more pancake ice on the Missouri River now. You can see if you look closely, some of the individual forms are merging together into these larger accumulations and forming flows. So this is kind of the step right before forming like a large flow. You can see this process pretty clearly in the top right of this picture. We can see a flow clearly made up of these smaller pancake ice accumulations that have merged together. In this picture, we see the formation of large flows moving downstream. These span most of the open water and will move downstream until they're arrested by accumulation downstream, or they might interact with border ice and slow down and stop. You can see in this case, it looks like these flows are going to run into this accumulation just downstream of the bridge and probably start to form an ice cover. Here's an aerial view of that same process going on. Note the clear lines. Hopefully I can get my mouse out here. Yeah, so there's like these clear lines where the border ice can be seen, kind of restricting the channel that these flows are moving in. So you can imagine that these zones can get congested and eventually these flows can stall. So here's an older example of a very large Frazil ice flow on the Yukon River. It's likely that these flows eventually stopped and formed a continuous ice cover. The eventual ice cover structure will have artifacts from this kind of extrusion process that you can see. These ice forms are pretty interesting, that are kind of being shoved out just based on the channel geometry into this wider bend. Okay, so this is that cartoon again of the Frazil ice. We've covered the basic processes of anchor ice formation, Frazil slush, and flow formation. So also to note, Frazil can remain entrained in the flow too and move downstream. So it doesn't have to go into either of those categories yet. Last, we'll talk about the formation of stationary ice cover. This is pretty straightforward. The surface ice forms that we just went through can and usually do form a continuous stationary ice cover that's floating, but prevented from moving downstream by forces along the banks and transfer of stress into ice cover downstream. So these ice covers will tend to form from the downstream up. There's a range of ways that this can happen exactly. We've broken things down into different categories that here we're kind of categorizing things based on the velocity of the river and often related to flow depth. So for slow moving rivers, bridging may occur. Border ice might grow across and narrow the channel, and further growth could either close off the cover just from that process, but often Frazil slush will concentrate and stall in the narrow zones between the border ice too and contribute to that in slower moving systems. Flows can continue to concentrate to the point where they no longer move downstream and they'll completely cover the water surface into what we call a juxtaposed configuration. So just imagine all those pancake ice accumulations being kind of grouped up. The individual flows will form a continuous cover. In faster moving rivers, underturning and shoving of ice covers are common processes where ice moving downstream will impact an intact ice cover and can thicken and be pulled under the ice or maybe ride up on top of the ice. These are pretty complex processes that are outside of the scope of what we're going to talk about today, but it's important to know that can happen. Flows in Frazil, sort of moving down a velocity, higher velocity systems, flows in Frazil slush can be carried under an ice cover and may just continue to move downstream if the current's strong enough. But in some cases, they may just stop and accumulate on the underside of an ice cover, essentially thickening it. In the case of Frazil ice deposition, if we're thinking about Frazil ice particles accumulating on the underside of the ice cover, it's actually a very similar process to sediment deposition, just upside down. Instead of the particles accumulating on the bottom because they're not buoyant and weigh more than water, they're buoyant, and so they're accumulating in bed forms that in some ways mirror sediment deposition on the bottom. If the stream or river is moving fast enough, an ice cover may not form at all, and thermal aspects can drive this as well. But that is a possibility. You might not get any ice cover. So here we see the formation of stable ice cover that form from individual flows. This cartoon here also shows the potential for under ice deposition. Missing from the figures are the larger flows that get pulled under relatively intact, but then become arrested, thicken the ice cover. I mentioned that, so they're not really shown here, but you can just imagine blocks of ice kind of stuck to the bottom of that ice cover there, and that does happen. Okay, once a continuous ice cover is formed, we refer to that as sheet ice. It may not, and it probably isn't a uniform thickness on most rivers, so it's not just one continuous thickness. We already discussed some of the ways that that continuous ice cover can form, but again, it's either typically from a thermal process of border ice meeting or from a Frazil ice driven freeze-up process. These figures here are a nice example of border ice forming sheet ice captured by an ice monitoring webcam that was installed on the Penderay River in Idaho. The first image, that's on January 4th of, I guess, I'm not sure what year, 2017. We see that the river is pretty open. There's probably some Frazil ice slush you can see on the shore, kind of in the reflection there. And then about a week later, border ice has closed off a lot of the river. And then just a few days later, 4 days later or so, the entire channel is covered. So this is a pretty slow moving river affected by hydroelectric dams. So it kind of behaves a little bit more like a lake than a river, but this is definitely a process that can occur. Okay, so last we'll step through ice formation in steep streams. We consider a steep stream if its average long profile slope is greater than about 1%. These streams are often characterized by gravelly, cobbly, and perhaps boulder-strewn substrate. These streams exhibit a common pattern of ice formation, but obviously this varies site to site based on environmental conditions. We'll talk about a typical pattern of ice formation on the next slide. Ice interacts with complex substrate and forms complex ice formations, which include anchor ice, ice dams, and border ice. So these figures here, this shows a possible progression of ice. Obviously, every case is different. Every site's a little bit different. But this shows a possible progression of ice progression in the steep mountain stream. And this is actually taken from a report on Ship Creek in Anchorage on J-Bear. The top left figure is what the stream looks like in the late fall. So the top part of each figure is the profile of the stream, and then the bottom part of the figure is looking at it in cross-section, looking downstream in cross-section. So in the late fall, on the first step one here, the flow is in recession and is probably pretty low, pretty shallow. Moving to the right, in step two, we see cold air temperatures have created the conditions for anchor ice to form. The stage rises in the channel, and although the flow didn't increase, it might actually be decreasing due to recession. The anchor ice raises the effective bed surface, and the water flows on or sometimes around that. In step three, we see the initial formation of ice dams as water cascades over cobble and boulder steps in the channel. You can start to see this accumulation of ice on the face of those. Now moving down to the bottom left, in step four, we see that the ice dams grow and the stage of the stream continues to increase. At this point, there might be some out-of-bank flooding occurring even with pretty low flow conditions, because we've got a lot of ice in the channel now and there's not as much area for the water to flow. These dams can create pools of slower moving water and will allow Frazil slush to accumulate, and then thermal ice processes can take over. Now we've got this kind of slower moving water behind these ice dams. And that's what's depicted in the solid blue there. That's a solid surface ice that's starting to form in certain locations. And now in step five, the ice dam growth tends to stop once surface ice cover forms and provides an insulated lid over the channel. This step really changes the dynamics of the process. Once the ice cover forms, the heat transfer from the stream water into the air slows down a lot because you've got this lid insulating it. This will cease the formation of Frazil ice, so you're not getting any more Frazil. And then newly arriving stream flow isn't losing heat as much and can tend to erode the anchor ice and the ice dams. So in step six, we see the flows actually return to the bottom of the stream. In this particular example, extensive anchor ice remains under the ice cover and supports it, but this often isn't the case. An observer will see something that we don't have depicted here, like in a step seven, but where the surface ice would actually collapse due to the lack of support from anchor ice or buoyant support, because the water is now just at the bottom of the channel. An example of that, this is just a figure showing a collapse and partially suspended ice cover following the breach of ice dams under the ice cover. So this is a really common process that a lot of you have probably seen on steeper mountain streams, where you have this kind of perched ice cover and then the stream flowing at the bottom. And it's not because there's a lot of flow, it's because there was ice buildup and ice formation, and then the thermal processes changed and the ice cover collapsed. So ice processes in steep streams is an interesting and really complex topic on its own, but for now, we'll leave it here, and I think maybe somebody later in this series is going to talk a little bit more about that. So we covered a fair amount of ground here. We started with the basics of water and ice that are important to understand when we're thinking about the bigger processes of river ice formation. Talked about thermal ice growth, talked about the complex formation of Frazil ice, and then we discussed the ways that ice covers form. And then we also briefly touched on steep stream ice formation. So with that, I guess I'm right on the mark, maybe time-wise. I'm not sure, Aaron, if we have time for questions, but
yeah, we have about 10 minutes. We have about 10 minutes.
Okay,
you can take questions now if anyone.
Yep, that works. Nice one, Dale. Ice is so cool. I agree.
I had to.
Yeah, so if you have questions, I know we just covered a lot of material. You can feel free to either pass the questions through Aaron or, you reach out to me or Jeremy too. We're happy to chat about this stuff at any time.